So let's continue with some more examples, as examples and problems are the best way to learn some of these concepts, right? So let's take another question. So imagine we want to compute the number of numbers, right? The number of numbers between 100 and 999, which basically means three-digit numbers, right? Which do not contain 7, right? Which do not contain the digit 7, right? So these are three-digit numbers which do not contain 7, right? How do you solve a problem like this? Again, look at this. We have 3 digits. Remember that the first digit cannot be 0. The first digit cannot be 0, because if the first digit is 0, it becomes a 2-digit number. We want a number between 100 and 109, right? Which means we want only 3-digit numbers which do not contain 7. Now what all digits do I have? 0, 1, 2 up to 9, right? Now there are 10 digits here, right? But the first one cannot be a 0. It cannot also be 7, right? So how many options do I have here? It cannot be 0, because the moment it is 0, it becomes a 2-digit number. And we are asking the number of numbers between 100 and 999 which do not contain 7. So how many possibilities are here, right? So here there are only 8 possibilities. In the second digit, this digit can contain a 0. Nothing stops us, right? But it cannot contain 7, which means there are 9 possibilities here. Similarly, there are 9 possibilities here, right? So how many total possibilities are there? 8 into 9 into 9, right? So this is 9 9s are 81, 81 into 8, right? 81 into 8 is 8, 8 8s are 64. Now in probability, when we learn probability, we'll come across problems like this, which is, if I randomly pick a 3-digit number, from 100 to 999, what is the probability that that number does not contain 7? Again, we'll revisit such problems when we learn probability. Such problems are solved very simply by using combinatorics. How do we solve them? The probability that a random number that we pick between 100 and 999 does not contain 7 is very simple, right? It is the total number of numbers which do not contain 7 divided by the total number of numbers that are here. Look at this. There are 900 numbers here. Some people may get confused and say that there are 899 numbers. No, it also includes 100, right? So there are a total of 900 numbers. So the probability of randomly picking up a 3-digit number which does not contain 7 is 648 by 900. Again, this is something which is useful again in probability, right? So now let's look at another question, right? So imagine I have 5 boys and 4 girls. Imagine I have this set of students or kids, right? I want to arrange them. So let's look at multiple cases here, right? I want to arrange them in such a way that no two girls are together. Okay, no two girls are seated next to each other, right? Are seated together. In how many ways now can I arrange 5 boys and 4 girls? Remember, each boy is unique and each girl is unique, right? Now I have 5 boys and 4 girls. So let's actually see how to tackle this problem. First, I will place 5 boys, right? So I have 5 boys here. Obviously, each boy is distinct. So in how many ways can I arrange 5 boys? I can arrange 5 boys in 5 factorial ways, in 5 positions. Now, once I have placed 5 boys, since no 2 girls should be together, I can place girls in these locations. Imagine if I place a girl here, another girl here, another girl. See, if I limit myself to placing girls only in these blanks, right? And in each blank, I'll only place exactly 1 girl. Then no 2 girls will be seated next to each other or will be seated together, right? Now, how many positions do I have here? 1, 2, 3, 4, 5, 6. Now, first I have to arrange my 5 boys. I've arranged them in 5 factorial ways. Now I have 6 locations and I have 4 girls to be placed, right? I have 6 locations and I have 4 girls, which means of these 6 locations, I have to pick 4 locations, or I have to choose 4 locations where I'll place these 4 girls. In how many ways can I choose that? 6C4. Amongst these 6 locations, I have to choose 4 locations. And in those 4 locations, I have to place the 4 girls. In how many ways can I place the 4 girls? I can place them in 4 factorial ways. Right? Again, what is this? Again, if you notice, this 6c4 into 4 factorial is nothing but 6p4. Right? Look at how I've broken this problem into multiple subparts and started tackling them. Right? So let's take another case, right? Just so that this concept is much better understood. What if I say no 2 boys are together? So what if I say no 2 boys are together? In how many ways can I now arrange? Right? Now, as we know, there are 4 girls here, which means I can arrange 4 girls. First, let's arrange 4 girls. I can arrange 4 girls in 4 factorial ways. When I arrange 4 girls, look at which all locations I can place a boy. Because I don't want 2 boys to be together, I'll place 1 boy in each of these locations. And I have 5 locations here, right? I have 5 locations here and I have 5 boys. If I have to place 5 boys in 5 locations, in how many ways can I do it? 5 factorial ways. So 4 factorial into 5 factorial is the number of ways I can arrange such that no 2 boys are together. Now, let's look at a slightly different case now, right? What if we have a particular set of girls, a particular pair of girls, let's say a particular pair of girls. Let's assume a particular pair of girls want to sit together. So 2 girls always want to sit together. They always want to sit together. If this is the requirement or if this is the constraint that I have to work with, that a pair of girls always want to sit together, then how do I count? See, initially, how many boys do I have? I have 5 boys and 4 girls. This is what I have. But let's assume there are 2 girls. Let's call them G1, G2. Okay, let's assume there are these 2 girls who always want to sit together. So if I treat them as one unit now, I have 4 boys, right? And I have 3 girls. These girls can be individuals or a single unit like this. Right? Look at this. I'm treating G1, G2. This is a particular pair of girls that want to sit together. So I'm treating them as one unit. Right? Now look at this. In how many ways can I arrange 5 boys and 3 girls? Look at this. This is again very simple. So which means I have a total of 8 people. I have no other constraints that no 2 boys should sit. I don't have any other constraints. The only requirement is a particular pair of girls always want to sit together. So I have 8 distinct individuals. One of these individuals is a pair, right? One of these units is a pair. So in how many ways can I arrange 8 items in 8 locations, 8 factorial ways? But wherever I place this unit G1, G2, I could actually place this as G1, G2, or I could also place them as G2, G1. Right? There are 2 possibilities. Wherever I have placed, in whichever location I have placed this single unit, which I'm treating as one unit. That's why I have, instead of 4 girls, I have only 3 girls here. Because 2 girls are individuals and 2 girls form one unit pair. Right? So between these 2 girls, I had 2 possibilities of arranging them. G1 could sit before G2 or G2 could sit before G1. Right? There are 2 possibilities here. So this will get multiplied with 2. So the number of ways in which a particular pair of girls always sit together is 2 into 8 factorial. And look at how simply we are deriving all of these things. Okay, let's look at a slightly different variation of this also. Okay, a slight different variation of this is, in how many ways can you arrange such that a particular pair of girls never sit together? A particular pair of girls do not sit together, right? Do not sit together. How do you tackle a problem like this? Right? For example, let's assume I have girl 1 and girl 2 who for some reason don't want to sit next to each other. This problem I can write it as the total number. Look at this, the total number of ways I can have all these. See, I have 5 boys. I have 5 boys, right? Yeah. I have 5 boys and 4 girls, right? The number of ways in which I can arrange these 9 individuals minus the number of ways in which so minus the number of ways or number of arrangements where these girls, where this pair of girls, where this particular pair of girls always sit together, right? I can always write this like this, right? Always sit together, right? So what is this equal to? What is the total number of ways I can seat 9 people? 9 factorial ways. 9 factorial is the number of ways I can arrange 9 people, right? Minus, here we've already computed, right? Where a particular pair of girls always want to sit together. And that is 2 into 8 factorial minus 2 into 8 factorial, right? Now what do I get? This is the number of ways in which a particular pair of girls do not sit together ever, right? So again, we have broken this bigger problem into the total minus the number of ways in which the pair of girls can sit together, because this is easier to compute. This part, which as we have just seen, is fairly easy to compute, right? So now, so these are some examples. More examples. Let's work on more examples. Let's go back to our Mississippi example, right? So we have seen this in the previous video, right? Mississippi. Again, this is a very, very good example, right? I have 1M, I have 4 I's, I have 4S, and I have 2 P's in this, right? Total of 11. Now, right? Now imagine I want some, again, again, this is a very, very nice example which is used in tons of textbooks also. So let's start counting from here. Suppose if I want to count the number of ways in which I can rearrange the words, so rearrange the characters in this word. In how many ways can I arrange each of the characters in such a way that no two S are together. I don't want S to be together, right? I don't want S to be together at all, right? Now, how do we do that? So first, let's ignore S. Okay, so I'll break this problem into multiple parts. First, let's ignore S. Then I'm left with 1M, 1I, and 1P. So total of 7. First, let's arrange these 7. In how many ways can I arrange these 7? Again, this is permutations with limited repetitions. This is 7 factorial by 4 factorial into 2 factorial. We've already seen this. Okay. Again, remember, I have not yet handled these S here. Now, I have placed 7. Look at this. I've placed 7 characters. Let's assume these characters are C1, C2, C3, C4, C5, C6, and C7. Of course, some of them are repetitions because P repeats twice, I also repeats twice. Now, if you think about it, I don't want I have 4S, right? I have 4S. I don't want any 2S to be together, which means, think about it. Look at it. What if I place 1S here? Let's create these blank spaces in between these characters. Okay. What if the 4S that I have, in each of these blank spaces, I'll place exactly 1S. Nothing more, nothing less. Okay. So nothing more. I could place less also. Sorry. Okay. Because I have 4S, and how many gaps do I have? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positions. And amongst these 8 positions, I can choose any 4 positions and place it in such a way that 1S is placed in each of these 4 locations. For example, if I pick this location, this location, this location, and this location, then I'll place an S here, I'll place an S here, I'll place an S here, I'll place an S here. Okay, so it's possible to have 1S or 0S in these blank spaces. And because each of these S are the same, see, this S and this S are one and the same. They're the alphabet S. There is no way to distinguish them, right? So now in the second part, these are the number of ways I can create. These are the number of ways I can arrange the rest of the 7 characters that I have except S. Now I can place S. In these 7 length in these 7 length strings. I can place my S such that no 2 S are together in 8C4 ways. Look at this. 8C4. Why is it not 8C4 into 4 factorial? Because whether I have this S here and this, because all these are same S here. They are the same character, right? It's a repeated character. Don't forget that, right? So now what am I doing? In my second step, I'm picking 4 out of 8 positions and placing my S there. So what is the total number of ways in which I can rearrange this string such that no two s are together. It is 7 factorial by 4 factorial into 2 factorial into 8c4. That's it, right? This is a slightly tricky but a very interesting question. Okay, so let's look at more questions like these. Okay, so let's say I want to build some binary strings. The number of binary strings, okay, I want to build a binary string. The number of binary strings that I can construct, again, this is a simple example, with n zeros and n ones, right? Such that 0 and 1 are always alternating. Look at this. My 0 and 1 are always alternating. I cannot place two zeros together or two ones together. I want to construct a binary string which has n zeros and n ones such that my zeros and ones are always alternating. And how many ways can I do it? I can only do it in 2 ways if you think about it, right? Because I can have a situation where my zeros are in even positions. My zeros are in even positions, right? Let's assume n equals to 3. Just for simplicity, let's assume n equals to 3, right? Then or my zeros are in odd positions. Okay. If my zeros are in odd positions, my ones will be in even positions because zeros and ones are alternating. If my zeros are in even positions, my ones will be in odd positions. It will be like this, right? 1 0 1 0 1 0 or 0 1 0 1 0 1. There are only 2 strings that I can construct. See, if n equals to 3, I'm just constructing an example for n equals to 3. But this is true for any n. For any n, if I have n zeros and n ones, and if I want to construct binary strings such that ones and zeros are alternating, I have only 2 options. Ones in even, and which obviously means, zeros in even, which means ones in odd, obviously, right? Odd position. Similarly, zeros in odd and ones in even position. They both are equivalent concepts if you think about it, right? So zeros in odd basically means 1 in even because you want them to be alternating. A very simple example. Just wanted to bring up slightly different examples also. Now let's think of another example, right? Imagine if I have 5 boys and 6 girls. Okay, I have 5 boys and 6 girls. I want to arrange them. I want to arrange them alternatingly. I want to arrange them alternatively, which means no 2 boys are going to sit together, no 2 girls are also going to sit together. Now let's think about it. So I have 5 boys, right? So let's take the smaller one of them. 5 boys and 6 girls, right? Yeah. This 6 is not boys, 6 is girls. Okay, so I have 5 boys, B, B, B. In how many ways I can organize 5 boys? 5 boys I can arrange in 5 factorial ways. Now, after I've arranged 5 boys, I want to arrange my girls. Look at this. My girls, I have 6 girls, right? I have my 6 girls and I have 6 positions here. Look at this. If I start arranging them alternatively, I have exactly 6 positions. Remember, each boy is unique and each girl is unique, right? So if I arrange them alternatingly, I have 6 locations and I have to place 6 girls. And each girl is distinct, which means I can arrange them in 6 factorial ways. So here, unlike here, because here what's happening is your zeros are identical to zeros, your ones are identical to ones. But here your boys are unique, each boy is unique and each girl is unique here. That's the important differentiation. The next very interesting concept are called circular arrangements. Very interesting concept. Okay, so what we have seen till now are called linear arrangements because we are arranging people in a line or in a linear structure like an array. Till now, if you think about it, I'm arranging everything in a linear way. I'm not arranging them in a circular fashion. Imagine if I have to arrange these people in a circular fashion, what happens? Those are called circular arrangements. Okay, let's see how they work. It's very interesting. It's a very interesting part of permutations. Okay, let's understand this with examples. So imagine if I have 5 boys. I want to arrange them in a circular table. Okay, in how many ways can I arrange them? Look at this. Imagine, so forget about the fact that it's circular. in how many linear, if I were to arrange them in a linear fashion, like in a line, right? I have 5 positions or 5 chairs and I have 5 boys. In how many ways can I arrange them? 5 factorial ways. First step. Second step, once I've arranged them, see, look at this. Imagine if I've arranged them like this: B1, B2, B3, B4 and B5. Imagine that I've arranged them this way. Now I'll convert this linear thing into a circle. See, I can see if I just join this with this, I can construct a circle like this: B1, B2, B3, B4 and B5. See, the linear structure, I've converted them into a circle. Right? This is one way of arranging them in a circle. But the circular arrangement is equivalent to, because the circle, if I rotate the circle, it's still the circle, right? So in circular arrangements, this is same as B2, B3, B4, B5 and B1. So these two circular arrangements are considered equal in this case, because this circular arrangement is simply rotating this arrangement slightly, right? And this is equivalent to, look at this. This is, so in this location, so let's assume there are 5 locations here for simplicity. In this location, I could have B1. Now if I rotate this left, I'll get B2. Again, if I rotate this, what will I get? I'll get B3 here. I'll get B2 here. I'll get B1 here. I'll get B5 here and B4 here. This is also, and all these arrangements are considered equivalent in circular arrangements. In linear arrangements, look at this. In linear arrangements, they're not considered the same. In the linear arrangements, they're considered different. Right? Look at this. B1, B2, B3, B4, B5 is considered different from B2, B3, B4, B5 and B1. In linear arrangements, this is different from this. But if you circle them, if you convert this linear arrangement into a circle, you get this, right? If you convert this into a circle, you get this. If you convert this into a circle, you will get this. Now in circular arrangements, both of them are considered equivalent, which means now comes the fun part. How many such equivalent, look at this, for this structure, for this linear array or for this linear arrangement, how many circular arrangements are equivalent? That's very simple. This position, I can have B1. If I rotate it by 1, I get B2. If I rotate it once, I get B4. If I rotate it again, I get B4, again the whole circle. If I rotate it, I get B5. Right? So these 5 values, these 5 rotations or these 5 arrangements are considered equivalent in circular arrangements. So my linear arrangements are 5 factorial, but so in my linear arrangements, this is counted as 5 distinct arrangements. But in my circular arrangement, by definition, these are considered as only one arrangement. So the number of circular arrangements that I have is now 5 factorial by 5. That's because, look at this, that's because these 5 have to be treated as have to be counted only as one, not as 5 distinct values. That's why we are dividing it by 5, which is nothing but 4 factorial. Right? So this is the number of circular arrangements. Remember, in circular arrangements, this is considered equivalent to this, which is considered equivalent to this. If you rotate it, if you get the same thing, if you rotate it, right, whatever you get is considered equivalent in circular arrangements. This is the tricky and interesting part. Okay, this is a very simple example. Again, I know some people who remember this formula by heart. Right? If you have n items, and if you were to arrange them in a circular table, the number of ways you can do it is n minus 1 factorial. But it is important to understand how we arrived at that formula. Arriving at that formula is a more important thing, because you may forget formulae today, but if you know how it's arrived at, this skill will help you derive the formula whenever you want. Right? So that's the first question. So let's take the second question. Imagine if I have 6 boys and 7 girls on a circular table. Look at this. I am trying to place 6 boys and 7 girls on a circular table. In how many ways can I do it? Now, look at this. I have 13 distinct items here, which I want to place on in a circular arrangement. How many ways can I arrange 13 distinct items on a circular table? I can arrange them in 12 factorial ways, or in other words, 13 factorial ways. by 13. Okay, again, I don't remember the formula, to be honest with you. I don't remember the n minus 1 factorial formula. I often write it like this. In how many linear ways can I arrange them? 5 factorial. But each of these 5 rotations should be counted as 1. Hence, I divided by 5. So that's a formula that that's how I actually derive it almost all the time in my head. Right? So let's look at some variations of this, right? So imagine if I have 6 boys and 7 girls in a circular, I want a circular arrangement, and let's assume I want all girls to be seated together. I want all girls together. In how many ways can I do it? Look at this. If I have all the girls to be seated together, I can think of them as one unit. Then I have to consider them as one unit. Now I have 6 boys. And 1 unit of all the girls, right? Which means I have 7 distinct elements now. Look at this. I have 7 distinct elements. In how many ways I can place these 7 distinct elements in a circular table? In 7 factorial by 7. These are the number of ways I can arrange these 7 distinct units or 7 distinct elements in a circular table. But then the 7 girls that I have, look at this, the 7 girls that I have, I can arrange the 7 girls in 7 positions. Even in a circle, let's assume this position, this, 1, 2, 3, 4, 5, 6, 7. Let's assume these 7 are the girl positions. Rest of the 6 are boy positions, let's say. Okay, amongst these 6, again, these 7 have to be together. Now, but amongst these 7 positions, in how many ways can I arrange the 7 girls? In 7 factorial ways. Right? So what is the total number of ways that I can arrange? See, this is the number of ways I can arrange 7 units in a circular table. Right? Now, once I've arranged them in a circular table, then these 7 girls that I have, in how many ways can I permute or arrange them? I can arrange these 7 girls in 7 factorial ways. So this is equal to 6 factorial into 7 factorial ways. Right? This is a very interesting example. Lots of fun to solve problems like these. Okay, so let's look at another example, right? Suppose if I have 6 boys and 7 girls, right? And 2 girls always want to sit together. 2 girls always want to sit together. Again, this is a case of circular. Suppose I have to arrange them in a circular arrangement, right? And, right, this is the first thing. The second thing is 2 girls always want to sit together. Now, in how many ways can I do it? Let's see. Okay. So let's simplify this problem, right? So I can think of this as 6 boys, 5 girls, and 1 unit which contains the 2 girls. Let's call these girls G1, G2. Okay. So total, how many distinct units I have? 6 plus 5 plus 1, 12 units. So 12 units or 12 items, if I have to arrange them in a circle, I can do it in 12 factorial by 12 ways. Okay, which is equal to 11 factorial ways. Now these 2 girls, look at this. These 2 girls who are placed in the circular loop, they can either be placed in such a way that G1 in a clockwise scenario, G1 is before G2 in this clockwise scenario, or G2 is before G1 in this clockwise order. These are 2 different arrangements. Rest everything being the same. Let's assume the rest everything being the same. G1, if you go from a clockwise direction, G1 before G2 is different from G2 before G1. Right? So there are 2 possibilities in which I can arrange these 2 girls who always want to sit together. Right? So this multiplied by 2. So 2 into 11 factorial is the number of ways I can arrange 6 boys and 7 girls in a circular fashion where 2 girls always sit together. That's it. Very simple, nice example. Let's look at another example, right? So, okay, so let's modify the problem slightly. Again, 6 boys, 7 girls, circular. Okay, we'll talk about circular right now, and no 2 girls. So no 2 girls are seated together. Okay, this is a slightly more involved example. No 2 girls are seated together. Okay, so let's see. So I have 6 boys first. I have 6 boys, right? So boy 1, okay, boy, 4, 5, 6, right? Let's see, because I don't want any two girls to be seated. I can seat a girl here. I can seat a girl here, 3, 4, 5, 6. Because it's a circular thing, there are only 6 positions. But I have to place 7 girls. That's impossible, right? See, I have only 6 positions and I don't want any two girls to be seated next to each other. Look at this, I don't have 7 positions here because it's a circle. Because this is a circle, I have only 6 positions. If it were a linear thing, I would have had 7 positions and I would have been successfully be able to place them. Right? Since I have only 6 positions here, if I start placing the girls here, let's assume I place a girl here, I place a girl here, I place some girl here, one girl here, one girl here, one girl here. I'm still left with one more girl. Where do I place them? Whenever I place them, I'll break this constraint that no two girls are seated. So this is not possible. So this is not possible. Right? This is a very nice case which is not possible or impossible. Okay, let's take another example. Okay, so let's take another example now. Imagine I have a case wherein I have 6 boys and 7 girls and no two boys. Again, this is also a case of circular arrangement, and no two boys sit together. No two boys sit together. Now let's see. So we saw that if my question was no two girls sit together, it was impossible. But what about no two boys sitting together? Think about it, right? First I have 7 girls. Okay, first let's place the 7 girls in a circular loop. Okay, so let's place 1, 2, 3, 4, 5, 6, 7. In how many ways can you place these 7 girls in a circular loop? 7 factorial by 7. Because each of them is a distinct girl, right? Now once you have done that, now comes the fun part. Now I'm left with 6 boys. Right? I'm left with 6 boys. Look at this. I can place a boy here, here, 3, 4, 5, 6, and 7. I have 7 positions where I can place 6 boys. Right? Now in how many ways can I pick them? So let's look at this. First, amongst these 7 positions, 1, 2, 3, 4, 5, 6, 7. Amongst these 7 positions, let me choose 6 positions. I'll choose 6 positions, which means I'll discard one position. Let's assume I discard this position, which means I don't place anything here. The rest of the 6 positions I've chosen. Now in these 6 positions, in how many ways can I place these 6 boys? I can place them in 6 factorial ways. Right? So this is nothing but 6 factorial into this whole thing is nothing but 7p6. That's all. Right? It's a very good example actually. Okay, so let's think of another case, right? Let's think of another way of thinking about it. So let's assume I have 7 boys and 7 girls. Okay, look at this. I have 7 boys and 7 girls, right? And this is in a circular. Let's assume this is a circular arrangement. I want them such that they sit alternatively. Is that even possible first? So this is the same number of boys and girls. Instead of 7, which is tedious to draw, let's assume I have 3 girls and 3 boys. Okay, girl 1, boy 1, girl 2, boy 2, right? Girl 3, boy 3. Yes. So if they're equal number, you can actually arrange them. Simply, I'm verifying that with a simple example, right? Now totally what do I have? I have 7 boys and 7 girls. First, let's place the 7 boys on this circular, in this circular array, or in the circular formation. In how many ways can I arrange 7 boys? I can arrange them in 7 factorial by 7 ways. So I have boy, 4, 5, 6, and 7. Next, I have 7 girls, right? Now, how many positions do I have? I can place a girl here, 3, 4, 5, 6, 7. So I have 7 positions and I have 7 girls. In how many ways can I place them? I can place 7 girls in 7 positions in 7 factorial ways. So what is the total number of ways I can place 7 boys and 7 girls in a circular formation such that boys and girls are alternating, which is nothing but 6 factorial into 7 factorial. That's it. Okay. Now let's take a slightly different but a very interesting and ingenious problem. Okay. Suppose I want to build a necklace. Let's assume I have 5 red stones, I have 6 green stones, and I have 3 yellow stones. Okay. And okay, let's assume this is what I have, and my stones are not identical, not identical stones. Okay, so they're not identical stones. Actually, if you think about precious gems, not all gems come in the same shape and size. So each of these red stones are also distinct. Each of these 6 stones are also distinct. Each of these 3 stones are also distinct. Now, in how many ways can I construct a necklace? Okay, so how many distinct objects are there? 6 plus 3 is 9, 9 plus 4 is 14. There are 14 objects, and we are trying to organize them into a necklace like this. Immediately, people will jump to a conclusion that the number of ways I can do it is 14 factorial by 14, which is actually incorrect. I'll tell you why. Okay, a lot of people come to the conclusion that it's 14 factorial by 14, which is incorrect, because let me tell you, a necklace also has this very interesting property, which is, imagine I have my red stone, my red 1 stone, my red 2 stone, my green 1 stone, and rest of the other stones here. Let's assume this is one ordering. This ordering, see, a necklace can be worn this way or the opposite way. So let's look at this way, right? If I invert this, so I get this. Now, when I'm counting in my 14 factorial by 14, look at this. In my 14 factorial by 14, these two are considered, look at this, these two are considered as 2 different orderings. Because here R2 is on the right side of R1. Here R2 is on the left side of R1. Right? Or in other words, R2 comes in clockwise after R1. Here R2 comes after R1 in counterclockwise direction. So in this counting of circular arrangements, we counted these two to be not equal. We counted these two to be distinct. But when you're building a necklace, or when you're constructing a necklace, this necklace, if I just invert it, if I just invert this necklace, it will become this, right? Because these stones, look at this, these stones, I'm assuming here that the stones are circular or the stones are round. Okay, here I'm assuming that the stones are round in shape, right? So I cannot tell whether this order is in this way or in this way, because a necklace can be flipped, right? A necklace can be flipped, which means direction, while constructing a necklace, direction is not important. Whether things are in counterclockwise direction or in clockwise direction or counterclockwise direction is not important. So only in the case of constructing necklaces, direction is not important. But remember, direction was important when we constructed circular arrangements. So necklace is a special type of circular arrangement, right? So the number of ways you can construct is not 14 factorial by 14. It is 14 factorial by 14, the whole divided by 2. Why is it 2? Because this and this, these are 2 distinct ones. These are 2 distinct circular arrangements. So in my 14 factorial by 14, I counted these 2 as 2 distinct arrangements. But when I'm constructing a necklace, I'll construct these 2. I'll consider these 2 to be same. That's why I'm dividing the whole thing by 2. So this will be equal to 13 factorial by 2. Okay, so necklaces is a very nice example, very nice special case of circular arrangements. Okay, now let's look at so let's think of this as case A. There is a case B. What is case B? So here we assumed that the stones are not identical. Let's assume that the stones of each color are identical. If the stones of each color are identical, which means these 5 red stones are exactly similar. These 6 green stones are exactly similar. These 3 white stones, these 3 yellow stones are completely identical. I can't distinguish between them. Now how many arrangements are there, or how many necklaces can I design? Let's break up this problem, right? So first let's see. I have 14, look at this. I have 14 ways in which I can do this. Okay. So first let's arrange these 14 values in a linear fashion. So first step, arrange these 14 in a linear fashion. Again, this is nothing but permutation with limited repetitions. Okay. So what is the way we discovered this, right? 14 factorial by 5 factorial into 6 factorial into 3 factorial. This is the linear way. Now if I make this circular, okay, so the moment I make this circular, what happens? 14 factorial by 5 factorial into 6 factorial into 3 factorial into 14. Right? This denominator in 14 comes because of the circular nature. Third, it's a necklace. which means direction doesn't matter. So because of the direction, I'll say the formula here is 14 factorial by 5 factorial, 6 factorial, 3 factorial, 14 into 2. So in this whole thing, this part is the number of linear arrangements. This part, so this is the number of linear arrangements. This came because of the circular arrangement. This 2 came because of the direction in the necklace. Right? So the number of, if the stones are identical, the number of necklaces that you can build is 14 factorial by 5 factorial into 6 factorial into 3 factorial into 14 into 2. Very interesting problem. Actually, this is a very, very good problem actually. Okay. So now let's tackle a slightly different problem now. Okay. So let's say zoom. Okay. So let's tackle another question, right? Suppose if I want to build, so let's take with the various variations of this. If I want to build a 4-digit even number, let's assume I want to build a 4-digit even number. Now, what are even numbers? Obviously, your 0. Even numbers have to end in 0, 2, 4, 6, and 8. It's a 4-digited number, right? Since it's a 4-digited number, this can't be 0. So, how many possibilities are here? There are 9 possibilities here. How many possibilities here? 10 possibilities. How many possibilities here? 10 possibilities. Because any digit from 0 to 9 can be here. But since it's an even number, there are only 5 possible values here. Right? So how many 4-digit even numbers are there? 9 into 10 into 10 into 5. So 100, 900 into 5, 4500. Similarly, the number of 4-digited odd numbers. Okay, look at this. 4-digited odd numbers. Again, the same story. Okay, you can also compute it because the digits in the odd are 1, 3, 5, 7, 9. Odd numbers have to end in these digits. This is also equivalent to the same formula 4500. Very simple. Now let's make this problem slightly more tricky. Okay. So I want 4-digit odd numbers. Let's assume I want 4-digit odd numbers with distinct digits. Right? With distinct digits. Okay, this is a slightly more intricate case. Okay, let's look at this. I have 4 digits here, and I know that the last digit has to have 1, 3, 5, 7 or 9. Okay, let's look at this. So let's assume first let's place the values here. How many possibilities are here? 5 values are possible here. Right? 5 values are possible here. Now let's look at this position. In this position, how many can I place? I can't place 0. 0 is ruled out. Because I cannot have duplicates because every digit is distinct. Whatever odd number I have placed here, let's assume I placed 3 here. I can't also use 3. So 3 is also ruled out here, which means I have only 8 possibilities here. Right? Next position, whatever is the digit that I have placed here, 1 digit is taken away because I want each of these digits to be distinct. So 1 digit is taken up here, 1 digit is taken up here, 2 digits are taken up. Here I can have a 0. So if from the 10 digits that are possible, 2 digits are already taken up. So 8 digits are possible here. Similarly, from the 10 digits, 1 digit is taken up here, 1 taken up here, 1 taken up here. So I'm left with 7 possibilities here. So the number of 4-digited odd numbers which are distinct is 8 into 8 into 7 into 5. That's it. Now comes a slightly different variation of this problem. Okay. So let's look at, so this is B, right? So the previous one was B, yeah. So let's look at a slight variation of this. Now if I want 4-digited even numbers with distinct digits. This is a slightly tricky case where people often make a mistake. Let's look at this. Imagine I have, look at this, if it's an even number, the last digit has to be 0, 2, 4, 6, 8. Right? Suppose here there is a small problem. Imagine if I place a 2 here, 2 or 4 or 6 or 8. If I place any one of them here, how many possibilities will I have here? Again, 0 cannot be here. Look at this. 0 cannot be here, right? Because then it will become a 3-digited number. If I picked up a non-zero number here, then one non-zero number is taken up, 1 0 is also cannot be here. So there are only 8 possibilities here. This is, let's call it case 1. Case 2. What if I have the same 4-digit, but in the last digit, let's assume I placed 0. Since all digits have to be distinct, how many possibilities are here now? 0 is already taken up, which means any of the other 9 digits can be here. Right? So there are two cases that you have to be very careful to handle here. One case is, again, this is all because of 0. Okay, because an even number can end in 0, but a 4-digit number cannot start in 0. It is because of this special case that you have to break it into two cases. I hope you understood this, right? So case 1 is, how many possibilities do I have here? 4 possibilities. How many possibilities here? 8 possibilities here. Similarly, 8 possibilities here and 7 possibilities here. So how many total possibilities here? 8 into 8 into 7 into 4. Now, this case is completely different from these cases. Because here I have 2, 4, 6 or 8 in the last digit. Here I'm fixing the last digit to 0. If I fix the last digit to 0, here you don't have anything that ends with 0. So these numbers are completely exclusive. These numbers and these numbers are completely different. If you think of them as two sets, they don't intersect. Right? So now the last digit is 0. There is only one way of placing this. This digit, I can have any one of the 9 possibilities, because 0 is already here. I have 9 possibilities here. Right? Here I'll have 8 possibilities. Here I'll have 7 possibilities. So how many ways now? 9 into 8 into 7 into 1. So what is the total number of 4-digited even numbers which have distinct digits? All of these plus these. So the final answer is this. Again, this is a problem where a lot of people make a mistake, and this case is tricky because of the 0 case. Right? So I hope you understood this. Again, this is a very, very interesting special case. Okay, so now let's go on to the next problem. So imagine if I have 5-lettered word. Suppose if I want 5-lettered words. Suppose if I want 5-lettered words with at least one A. Okay, 5-lettered English words with at least one A. Okay, how do we? So this is again, we'll solve a few related problems here, right? So the easiest way to think about it is, let's take all the total number of words that you can have. This is not circular. This is not about circular. These are simple arrangements. These are English words, right? So non-circular arrangements or linear arrangements. The total number of ways minus at least one A can be written as minus no A's altogether. This will give you, if I take all the English words, all the 5-lettered English words, how many are there? 26 power 5. How many of them don't have an A? See, if you remove A, there are 25 alphabets. So 25 power 5. So this is the number of 5-lettered words with at least one A. Because computing with at least one A is slightly tricky, we wrote it as total number of words minus no A's altogether. Right? No A's altogether. This is an easier way of rephrasing your problem and solving it. Okay. So if I want exactly one A, how do I do it? Let's solve this, right? So these are 5-lettered words, right? So first I'll fill 4 digits. First I'll fill 4 letters or 4 positions. In how many ways can I fill 4 positions? Again, when I'm exactly one A, right? Which means I'll avoid A here. So I can fill this in 25 ways. I can fill this in 25 ways. I can fill this in 25 ways and 25 ways. Because there has to be exactly one A, right? Now, which means now I'll place my A either here or here or here or here or here. So to construct the 4-lettered words, there are 25 power 4 ways. And when I'm constructing it, I'm ignoring A because I don't want 2 A's. I want exactly one A. So first I constructed the 4-lettered words, and then I will inject or I'll insert A in one of these 5 positions. In how many? See, I can, because I want exactly one A, I can place the A either in this position, this or this. So there are 5 ways or 5 positions that I have to pick one of these 5 positions and place the A here. So if I want 5-lettered words with exactly one A, it is 25 power 4 into 5, right? I hope you understood this. So now let's look at a slightly different case. What if I want at most one A? What does at most 1a basically means? It means 0a's and 1a's, right? 0a and 1a. Now let's see how many 0a's are possible. 0a basically means no a at all. If I don't want to have an a, if I want to construct a 5-letter word without a, it is 25 power 5, right? If I want exactly 1a, we saw the answer here, right? 5 into 25 power 4. So for at most 1a, I can write at most 1a as 0a's plus exactly 1a. And these two are completely different sets. Think about it. So if you think about all the set of words which contain 0a's, the set of words that contain 1a, there is no intersection between them. So I don't have to apply the principle of inclusion exclusion. They're completely two different sets. So I can just add them up like this, right? So now let's take a slightly different variation. So what if I have a case wherein I have at least 2a's? Suppose if I want at least 2a's, okay, can I write this as the total number of a's minus exactly 0a's, look at this, exactly 0a's plus exactly 1a, right? Imagine I have a case where I want at least 2a's, which means I need to have 2a's or 3a's or 4a's, so on and so forth. What is this? This is total minus 0a's and 1a. Then I have 2a's, 3a's, all the other stuff will come in the total, right? So what is the total now? Total is 26 power 5. We have seen 0a's. We have already used this, right? 0a's is 25 power 5. 0a's is 25 power 5. What is exactly 1a? 5 into 25 power 4. Again, we computed this here, right? Exactly 1a. 25 power 4 into 5. So if you want at least 2a's, which means 2a's, 3a's, 4a's, any number of a's, that will be total minus, of course, with repetitions, 0a's plus 1a's. Okay, this is a very simple thing. Now let's take a slightly different question. Again, this is a simpler question. Imagine if I want to construct a 10-letter word. Imagine if I want to construct a 10-lettered word where all characters are distinct, and I want to have 4 vowels. I want to have 4 vowels and 6 consonants. 6 consonants. In how many ways can I construct a 10-lettered word where each of the characters is distinct? It contains exactly 4 vowels and 6 consonants. Slightly intricate problem, but it's actually simple. So how many vowels do I have? A, E, I, O, U. 5 vowels. Because all the characters are distinct, I have to pick 4 of them. In how many ways can I choose 4 of them? 5 choose 4. Similarly, I have 21 consonants. Because of the 26 English alphabets, 5 are vowels. So I have 21 consonants. Of these 21 consonants, I'll pick 6 consonants. So now I have a set of 4 vowels and 6 consonants, right? And each of these is distinct. Each of these vowels is distinct. Each of these consonants is distinct. Now look at this. Now I want to fill these 10 characters in 10 locations. In how many ways can I fill 10 distinct characters in 10 locations? 10 factorial ways. So the answer for this is 10 factorial into 5c4 into 21c6. That's it. Look at how we have broken down this complex looking problem into parts. First, I have chosen 4 vowels in 5c4 ways. Then I have chosen 6 consonants in 21c6 ways. Now I have 2 sets. I have a set of 4 vowels. And I have a set of 6 consonants. From this whole set of 10 distinct digits, I want to arrange them into a 10-letter word. In how many ways can I do it? 10 factorial ways. That's it. You can actually solve this problem in 10-20 seconds if you understand the concept of permutations well enough.